Welcome to the fifth part of Lecture 2 for SE 413, Engineering Design Optimization. We're going to cover two things in this final lecture component on mathematical preliminaries. First, we're going to talk about differentiation of matrix-based functions. Here we're going to use some of the same rules that you learned in Calculus 1 and apply them to functions that are defined using matrices. Second, we're going to look at Taylor series expansions. And in Calculus 2, you went through infinite series and infinite sequences, and during that experience, you focused on approximations of continuous functions of a single continuous variable. In this case, we're going to expand this capability and show how you can create Taylor series expansions for multivariate functions. But first, I will review univariate Taylor series expansions before we move on to multivariate Taylor series expansions. Let's start off our discussion looking at a simple example. And we're going to use this quadratic function as an example for differentiation, both looking at gradients and second derivatives of multivariate functions. The gradient of a multivariate function is defined as a column vector where each element of this column vector is a partial derivative of this function. And this vector is defined such that the first element corresponds to the partial derivative of the function with respect to the first variable. The second element is the partial derivative with respect to the second variable, and so on for a finite number of variables corresponding to the dimension of the input to this function. Now, for this specific function, we can perform differentiation using rules from Calculus 1, and we can identify what the partial derivatives are and then arrange them in this order as a column vector. In this case, the gradient is a function of x1 and x2. In other words, the gradient changes as we move around in the input variable space. We can think of a gradient as a first derivative of a multivariate function. Now let's have a look at a second derivative of a multivariate function. The second derivative of a multivariate function is sometimes called the Hessian, and this second derivative takes the form of a matrix. It's going to be a symmetric matrix, an n by n matrix, a square matrix, where n is the length of the vector x. And if we are looking at a two-dimensional case, we are looking at the second partial derivatives of the function with respect to the various combinations of the input variables. And so along the diagonals, we're going to have the partial derivatives, the second derivatives with respect to each of the individual input variables. And then in the off-diagonal terms, we're going to have the cross derivatives. By convention, we define the off-diagonal terms based on the row and column number of the matrix. Here, this implies that we take the partial derivative of f first with respect to x1 and then x2, and then we use the reverse direction, the reverse sequence x2 and then x1. But you might remember that this sequence doesn't matter, and these two off-diagonal terms are going to be equivalent. If we had a function of more than two variables, then we would have a larger matrix with more off-diagonal terms, or the number of diagonal terms is going to be equal to n, the number of input variables. Now, if we were to go back and have a look at the gradient, this gives us the first part of our second derivative calculations. We need to take a look at each of these terms. We can then differentiate the first term with respect both to x1 and then to x2, and then differentiate the second term with respect to x2. Once we make those calculations, then we can determine for our example function, this quadratic function, what the Hessian is. The Hessian then is a square matrix and a second derivative of a multivariate function. Something interesting about the Hessian is that if we are calculating this for a quadratic function, then the Hessian is always constant. Notice that the variables x1 and x2 do not show up in the Hessian, so no matter where we are in the input variable space, the Hessian is the same. And this is something that relates to curvature. The Hessian describes the curvature of the function. And if we were instead to apply the Hessian to a linear function, say a plane in two-dimensional space, then think about what the Hessian might be. If there's no curvature and the Hessian is related to curvature, what should that be? The Hessian of a function that looks like a plane is going to be 0. But in that case, the gradient of a plane, that's going to be constant. So no matter where we are in the input space, if we're looking at the gradient of a linear function, the gradient is going to be the same. It does not depend on where we are in the input space. It's often helpful to take functions like this, or expressions, and represent them in a more compact matrix-based form. For example, we can express a general quadratic function using the following formula. It's possible to go through and take our original function and find out what are the values of these coefficients a, b, and c such that this matrix-based expression is going to be equivalent to this expression that is multiplied out in a standard polynomial form. If I were to take a look at this first term, c, that's a constant term. This represents the component that doesn't change. If we have a look at the original function here, f of x, there is no constant term, so c is equal to 0. And then if we have a look at the linear term, this second term, we want the calculation of this linear term to produce the linear components of this function. So x1 plus 2 times x2. So how do we do that? We need some vector a that has coefficients that we multiply by x1 and x2. Well, what's the coefficient of x1? That's just 1. What's the coefficient of x2? That's 2. So in this case, the vector a is 1, 2. We need to do a similar thing for this quadratic term, but in this case, we need to look at this complete calculation where we have x transpose times the matrix B, which is a 2 by 2 matrix, times x. We need to have x in there twice so that we can get quadratic components. With the vector x in there twice, we can get either x1 squared or x2 squared components, or we can also get the cross terms, x1 times x2. I'm just going to write in x1 and x2, x1 and x2 right there. Now, we want to produce a result that gives us 3 times x1 squared and 4 times x2 squared. Right off, we can see that if we don't have any cross terms, then the off-diagonal terms here are going to be 0. So now we need to figure out what are the terms that are going to produce a coefficient here of 3 and a coefficient here of 4. Well, it's simply 3, 4. You can go through and verify this for yourself. We can represent this original example function using this standard form and the definition that c equals 0, a equals 1, 2, and the matrix B is 3, 0, 0, 4. using that, let's see if we can arrive at the definition of the gradient and of the Hessian more rapidly. Originally, we calculated what the gradient and the Hessian were by expanding out all the partial derivatives. But we have some really nice patterns here in these quadratic functions. And let's see if we can take advantage of some of these patterns and extend some of the rules that we learned in Calculus 1 to multivariate functions represented using these nice matrix-based forms. Suppose we want to calculate the gradient of f of x directly from this matrix-based form up above. Well, let's see if we can apply the same concepts, things like the chain rule or the power rule, and see if that produces a result that's correct when treating these different components of this function the same as or similar to as we would if these were scalar quantities. Let's see if we can calculate the gradient of f of x more directly using the special structure it has based on the form here where we've represented this function using matrix-based expressions. We're going to see if we can think back to the rules for differentiation that we learned in Calculus 1 and extend them and see if they apply to these matrix-based expressions and then verify whether they work. So let's look at each of these terms one at a time. We have the first term, the constant term, the linear term, and the quadratic term. We're going to look at analogs of constant, linear, and quadratic expressions and their derivatives, and then see if we can take the rules that apply there in the scalar case and extend them to apply to this matrix-based set of expressions, and then check and make sure that it works. So let's suppose that we have three different functions: a constant function, a linear function, and a quadratic function. And I'm going to call these functions here alpha 1 of y, alpha 2 of y, and alpha 3 of y. Now with alpha 1, that's going to be our constant. I'm just going to call that c. It's a constant function. It actually does not depend on our independent variable y. And then alpha 2, that's going to be our linear term, and I'm going to define that as a times y. But here I'm specifying that y is a scalar. It's not a vector as with x. So it's in the one-dimensional space of real numbers. For alpha 3, I'm going to define that as b times y squared. What are the derivatives of each of these functions? With alpha 1, the first derivative with respect to y of alpha 1 is the derivative of this constant. Well, that's just going to be 0. Let's have a look at alpha 2. What's the derivative of a times y with respect to y? That's simply going to be a. And then if we look at alpha 3, b times y squared, what's the derivative of alpha 3 with respect to y, where both b and y are scalars? Using the power rule, we can say that this is equal to 2 times by. With that in mind, let's go back to the matrix-based function and see if these ideas extend. Well, the constant term that we have, the derivative of that with respect to the vector x, that's going to be 0. There's no contribution from a constant term. And then the linear term, this a transpose x, what would be a similar analog to this a times y? Well, maybe just a. Instead of having a scalar result, we have a vector result, but it is constant. And then this third term, the quadratic term, here we have what's essentially a constant, so the B matrix is a matrix valued constant, multiplied in a specific way with the x vector twice. So we're going to have these x squared terms resulting. So this is really like this scalar case, and I wonder if we could use the same power law in differentiating this quadratic term. So using the power law, we take this square and we bring it down and multiply that by the coefficient, and then we reduce the power by 1. So if we were to do that, what would this term look like? Well, we bring down the 2 and we multiply x transpose times b. Now we need to go back and see if this actually works. We know what the result needs to be. The gradient of f of x is 1 plus 6x1 and then 2 plus 8x2. Let's have a look at plugging in the numbers and seeing if this actually works for the gradient. We can ignore the 0, of course, and we're going to have first the components of a. We're going to have 1, 2. But then we're going to add to it the result of this multiplication. And if I were to go through and do that, we have this x transpose times 3, 0, 0, 4, x1, x2. And if we do that, then I realize I made a mistake with the dimensions. Actually, I needed to drop this term x and keep this term x over there. And so we're not multiplying over there. To keep all of the matrices consistent, I need to say that's x1, x2. And so then the components of this multiplication are going to be 3 times x1 plus 0 times x2, and then 0 times x1 plus 4 times x2. So this is the resulting vector, and then we need to plug that in, add it to the vector a, and remember to multiply by 2. So 2 times 3x1, that is 6x1, and 2 times 4x2 is 8x2. Oh, that's exactly what we were hoping to get. It matches the result that we deriving the gradient using the methods that you learned from Calculus 3. Let's have a look and see if this works also for the Hessian. One way to think about the Hessian is it's going to be the multivariate derivative of the gradient. And the gradient here is a vector-valued function. And for each component of the output of this function, if we are looking at the gradient of each component, then that is going to be a vector. And if we have multiple components that we're computing the gradient for out of this function, then it's going to be a matrix. So let's start off thinking about this gradient and then differentiating that gradient. If we take the derivative of this first term, this is a constant term, so that's going to go to 0. And then with the linear term, we can see that using the power law, we're going to, well, multiply this coefficient by 1 and then reduce the power of this by 1. So that's going to go to 1. So the Hessian, therefore, is going to be 2 times b. And then if we go in and plug in the value of b, we're going to get a result of 6008. And that matches what we derived originally for the Hessian. So we've verified that this approach works. This is not a formal development, but it is a really helpful trick that we're going to be using in the derivation of optimality conditions and other aspects that we're going to cover in this class. Another type of differentiation of multivariate functions that you're going to need to know is something called the Jacobian. A Jacobian is a first derivative of a multivariate vector-valued function. And we actually did something very similar to this. We looked at the gradient of f of x, and the gradient of f of x turned out to be a vector-valued function. It had two output arguments, or it produced a column vector of length 2. And then when we took the first derivative of the gradient, it produced the Hessian, which was a matrix. And so in this case, in general, if we have a vector-valued function and we are differentiating it, then we produce this Jacobian. And this Jacobian, by convention, has a particular form, and we're going to learn what that definition is. But this is something that is central to the theory for constrained optimization. So think back to our original nonlinear programming formulation. Minimize f of x with respect to x subject to h of x equals 0. We can also have inequality constraints. G of x is less than or equal to 0. Something that we pointed out is that the objective function is scalar, but the constraint function could be vector valued. We are interested in the gradient of the objective function when we are deriving optimality conditions. It turns out we are also going to be interested in the first derivative of the constraint function, but if this constraint function is vector valued, if it has more than one output, what does its first derivative look like? The answer is the Jacobian. Suppose we are differentiating this constraint. What if we have x of dimension n? And what if the output of h has dimension m? That is the number of equality constraints. If we first define more precisely what the vector-valued function h of x is, h1 of x, h2 of x. So h1 and h2 are scalar-valued outputs that are components of the vector-valued function h of x. And if m is the number of components or the number of constraints, then the last element of this vector-valued output is going to be the mth component, h sub m of x. If we want to get the Jacobian of this, the first derivative of this vector-valued output, we can write the Jacobian as j of x. So in general, this is a function that could depend on x. It's a matrix-valued function that could depend on x. And the norm that we use in arranging the first derivatives is each row of this Jacobian, the Jacobian matrix, is going to be the transpose of the gradient of the corresponding output of h of x. So we take the transpose of the gradient of the first element, and that becomes the first row of the Jacobian matrix. And then we do the same. We take the gradient of h2, there's the transpose, and we keep going until we get to the gradient of the mth output of h. So what is the dimension of this matrix? Well, obviously the number of rows is going to be m, but how many columns are there? If we take the gradient of a function and the dimension of the input vector is n, then we're going to have n outputs when we're calculating the gradient. So we're going to have n columns, and the Jacobian is going to be an m by n matrix. Based on the definition of the gradient that we went through before, we can write this out in a little bit more detail just to make sure it's completely clear. So systematically, as we move down the matrix, we are looking at partial derivatives corresponding to different elements of H. So the first row of the Jacobian corresponds to H1, the second to H2, and so on. But if we're looking at this first column, we are always looking at the first, or the partial derivative of H, the component of H, with respect to x1. But then as we increase the column that we're looking at, we are increasing the index of the input variable that we were taking the partial derivative with respect to. But say for column 1, we're always looking at h1, and then at this last column and the first row, we have the partial derivative of h1 with respect to the last element of x. And then finally down here in the bottom right, we're taking the partial derivative of the last output of h with respect to the last input variable xn. Let's move on to the next topic of Taylor series expansions. First, let's have a look at this in the context of functions of a single variable, and then we'll have a look at what the Taylor series expansion looks like for multivariate functions. This is a formula that you should be familiar with. This is something that is typically covered in Calculus 2, and this is an infinite series or an infinite summation. And it's possible to show that an arbitrary continuous function can be represented exactly using this infinite series, where f is the function, the original function, but evaluated at a specific expansion point, x0. And this symbol indicates the nth derivative of the function f, and we're looking at n varying from 0 to infinity. And that's divided by n factorial. And then here we're looking at the distance from the expansion point to the point that we are interested in evaluating the function at, and then that's taken to the power of n. So this infinite series can represent continuous functions exactly, but it's not always possible to use the infinite series in a practical way. And for a lot of numerical methods, it works out really well to use some kind of function approximation as the basis for numerical calculations. And so what we're going to do here is look at a truncation of the Taylor series, and that's going to give us an approximation of the original function. The formula is almost the same. I have just replaced the limit of this summation with k. So instead of summing from n equals 0 to infinity, we're going from n equals 0 to k, which is a finite positive integer. Also, I've indicated using this hat symbol that this is an approximation of f of x, or I could say that f hat of x is approximately equal to f of x, or it's equal to f of x plus the truncation error, because we've truncated off the rest of the terms that are larger than k. There are a number of properties to make sure to remember. In both of these cases, we are calculating the function value or an approximation of the function value that is based on an expansion point, x0. And using this expansion point, we need to calculate a number of things, including the distance between the expansion point and the point of interest where we want to evaluate f, or the approximation of f. And then we need to also calculate all of these derivative values before this formula is of any use to us. You may remember that the closer we are to the expansion point x0, the more accurate the Taylor series approximation tends to be. In addition, the number of terms that we use, or in other words, what is the value of k, that also has an impact on accuracy. As we have a larger value of k, that increases or improves the accuracy of the approximation. In the course notes, I have a number of examples that show cases where we're looking at different orders of approximation using the univariate Taylor series approximation. So we look at a constant approximation, k equals 0, a linear approximation, k equals 1, or a quadratic approximation, k equals 2, and we can see how increasing the order of the approximation improves the accuracy, especially as we move farther away from the expansion point. I'm not going to go through those examples in detail here, but I encourage you to go back to the notes, have a look through those, and if it helps, go back and review this section in calculus to make sure that you're comfortable with Taylor series expansions. But one of the key points here, one of the things to make sure is part of your perspective is to think of the Taylor series expansion as a function approximation. We're going to use this finite series, the truncated Taylor series, as a function approximation. We're going to do a number of different things with it, including using it as a function approximation that allows us to derive some properties that are important for optimization, including optimality conditions. The last part was review. Here's the new part, at least for most of you. We're going to be looking at the Taylor series expansion, but for functions of more than one variable. And to do that, I'm going to define a few different terms that's going to help this be a lot more compact and easier to explain. I'm going to use notation from the textbook Principles of Optimal Design by Papalambros and Wild. It's now in its third edition. This is one of the optional recommended textbooks for the course. Here I'm defining two different terms, and these are going to be useful in defining the multivariate Taylor series expansion. The first is the perturbation vector. It uses this symbol from partial derivatives, but it's defined differently. And here we're just specifically saying this is equal to the vector between x and x naught. So here x and x naught, these are of dimension n. Partial x, that refers to the perturbation vector. It's vector valued, and that's a vector that points between x and x naught. And then the second term is the function perturbation. This is the difference in the function value calculated between x and x naught. If we are thinking back to the different orders of expansion for the Taylor series, we can draw a parallel here and do this for the multivariate case. Using these terms, I can write that the perturbation vector is approximately equal to the gradient of f calculated at the expansion point x naught, which is a vector, multiplied by the perturbation vector. So this is similar to the first order expansion, or the truncated Taylor series expansion with just the constant and the linear term. But one question you might have is, well, where did the constant term go? If we think about the definition here of the function perturbation, that includes the constant term. We've basically just wrapped it up into a single term. We could redefine this then as f of x minus f of x naught is approximately equal to the gradient at the expansion point times the perturbation vector, and then move the constant term over to the right-hand side. And then that matches with what we are accustomed to with the univariate Taylor series expansion, specifically the first order expansion, where we've truncated off the quadratic term and all of the other higher order terms. Now let's have a look at a second order expansion using this same concept. In this second order expansion, as with univariate Taylor series, we have, of course, both the constant term and the linear term. The difference is we're adding in the second order term, the quadratic term. So what does that look like? Similar to a quadratic form, we're going to have the perturbation vector transpose times the Hessian, so the second derivative of the vector valued function f, evaluated at the expansion point, times the perturbation vector. Now it turns out that we need to have a coefficient out here of 1/2, so that if, say, we were to differentiate this, then we would no longer have this factor of 2 that comes from the power of 2 related to this quadratic term. One of the key takeaways here is that we've just derived two important approximate models for a continuous function f of x. The first model is a linear model of f of x. We're essentially fitting a tangent plane to the surface of an arbitrary multivariate continuous function and using that tangent surface in a variety of ways. It's going to give us information as we go through optimality conditions. Because it's a linear model, it can give us information about descent, what direction is downhill. But because it's a tangent plane being fit to a surface, it's not going to give us any curvature information. And that's important for determining whether we are at a minimum, a maximum, or something else. So we need a higher order model that we can use to approximate an arbitrary, continuous, nonlinear function so that we can do some analysis on that function that tells us something about curvature. So this quadratic model, this second order model, we're going to be using that in cases where we need curvature information. This concludes the third part of mathematical preliminaries. I hope the review and the introduction of these few important topics was helpful. Thank you.